Hi, welcome to OAI 5133 Advanced Distillation Design. And this is Lecture 6, De-Whiting Wall Distillations. What is de-Whiting wall column? Let us look at this thermally coupled prefractionator or Peugeot column. You have the prefractionator over here, liquid split, vapor split, and the main column. In fact, you can embed the whole prefractionator inside to one column, and we call it as a de-Whiting wall column. So what are the reasons to use a de-Whiting wall column? It can cause energy saving, incentive about 30% compared to the best simple sequence. And in fact, efficiency improves due to the prefractionation. On the other hand, it can cause capital saving incentive of about 30% compared to the best simple sequence also, which combine two columns into a single shell construction. However, de-Whiting wall columns has limited industrial experience. Only 12 columns built by BASF in year 1955, as well as PP Corriton Refinery, Sumitomo, as well as UMIT's pilot plant. On the other hand, thermally coupled prefractionator are actually used in the naphtha fractionation by the Razan Refinery, Russia. Besides, it is also facing industrial reluctance for exploitation due to lack of reliable design procedure, fear of control and operational problems, and unconventional technology perceived to have high risk. Let us look at the design procedure of the de-Whiting wall column. As shown in this slide, there will be too many degrees of freedom. Therefore, why do we not just simulate? For simulation, we need a shortcut design method for initialization and optimization. So, as shown in this flowchart, it will be started with shortcut design, then explore trade-off, initialize the design parameters, and have the rigorous simulations. So, the objectives of shortcut design of a de-Whiting wall are screening for the optimum column arrangement and initializations of operating parameters before rigorous simulations. As you have learned in the previous lecture, for the model development, you have to decompose the column. For example, you have the de-Whiting wall column over here. It will be decomposed to thermally coupled prefractionator and finally, three simple columns. And then these columns are thermodynamically equivalent. This slide shows the key features of shortcut design procedure. First, the model decomposes complex column into sequence of three simple columns like what you have seen in the previous slides. And then Fransky Underwood Gilliland's shortcut design method will be applied to each of the simple column. And then alternative shortcut methods can be used. Let us look at this three-column model. Column 1, 2, and 3. In column 1, a partial condenser string 1 and 2 from VLE and mass balance will fed into the column 2, whereby the liquid side streams is actually one plate above the feed plate. On the other hand, recoiler containing string 3 and 4 from VLE and mass balance will fed into the column 3 as a vapor side stream, which is one plate below the feed plate. So what is the connectivity of columns 1, 2, and 3? The conditions are satisfied both internal and external mass balance within the column and satisfies the product specifications. On the other hand, you have the equalized vapor flows for both the bottom of the column 2 and the top of the column 3. This slide shows the design optimization, whereby the design variables including distributions, number of plates, around 6 sections, reflux ratio, liquid split across the de-Whiting wall, and vapor split across the de-Whiting wall, as well as the feed condition. For the optimizations, all variables need to be optimized simultaneously, and it is a non-linear optimization, and the objective function is total annualized cost and operating cost. For designing the de-Whiting wall column, it will have the same degree of freedom as side stream column, as well as the same control configuration as side stream column as well. So this is the examples of temperature control of the de-Whiting wall column, as well as the composition control for the de-Whiting wall column as an example. Also, in the aspect of hardware, standard internals can be used in the column and insulate de-Whiting wall for better performance as well. Let us move to the case study, the replacement of the propenizer and deputenizer columns with a de-Whiting wall column, given the feed composition with the feed components as well as their mole fraction. The feed flow rate is 1,600 kmol per hour and 90% is liquid with pressure of 14.9 bar and temperature of 79 degrees Celsius. And then the product specification is shown in this slide with the top product, middle product, and bottom product. So as a top product is 94% recovery of N-propane, middle product 95% mole purity of middle products including I-butane, 1-butane, and N-butane. The bottom product contains 97% recovery of IC5. And this slide shows the assumption whereby you have the selections of key components, light key, middle key, heavy key, and lighter than light key, and heavier than heavy key. Also, ideal gas law applied, okay, to the method, all right? After the calculations or simulations, this slide shows the final design of separation of this mixture, all right? So this arrangement is pad yolk column, okay, which contain the top product, bottom product, as well as the middle product. The recoiler duty is 13,000 kilowatt with the reflux ratio of 4.8. This slide shows the comparison of energy consumption with sequences of simple column, including direct sequence and indirect sequence. Compared with the direct sequence, the energy saving of 20% can be achieved using the pad yolk column. In fact, additional capital saving will be achieved if a de-Whiting column is used. As a summary, de-Whiting wall column can reduce capital and operating costs relative to the best sequence of simple distillation column. Besides, shortcut design procedures provide good initialization for rigorous simulations, and standard column internals and conventional control strategy can be used. Let us move to the working sections number 6 on the de-Whiting wall distillations. Consider using a de-Whiting wall column in an existing process. This is the retrophic process, and the objectives are because of the process debottlenecking, energy saving, and product changes. On the other hand, like optimum utilization of existing equipment or hardware, or in order to have minimum investment on new equipment. And this slide shows the practical issues in column retrophic, including hydraulic capacity of existing columns. Existing column could be arranged in a different sequence as well, and some new capital may be required to supplement the existing equipment. If this has happened, additional capital costs will be incurred. On the other hand, downtime should be minimized as well. This slide shows the arrangement of the existing columns for NGL fractionation train case study, including the first column, the propenizer, second column, the butanizer, and the third column, the isobutanizer, to separate propane, C5, as well as isobutane and normal butane. And then you can see the recoiler duty for the butanizer and the isobutanizer as 3190 and 6970 respectively. Here are some considerations on the retrophic. The first one is the propenizer operates at a higher pressure than the downstream columns as shown in the previous slide. Operating it at a lower pressure would not allow overhead condensing using cooling water. On the other hand, operating the downstream column at a higher pressure would increase the difficulty of the separations. And let us consider only the debutanizer and the isobutanizer in our retrophic case study. Also, the deputanizer and the isobutanizer separate the feed into 3 products using the indirect sequence. Therefore, various prefractionator arrangements could be used instead. And then the feed data and product specifications in this case study are shown in this slides. So here you have the feed with those respective mole fractions. And then the bottom product of the first column is C5 plus. And in the second column, the isobutanizer, we have the top product of isobutane and the bottom product of the normal butane. The option 1 for the retrophic is to convert the isobutanizer to a dividing wall column, as shown in this slide. So the first column is still remain to separate propane, and then the isobutanizer column will convert to the dividing wall column, and you have 3 products over here: isobutane, normal butane, and C5+. The possible design implications of option 1 are existing hardware not fully utilized. This is because the butanizer mothballed or decommissioned. Extensive modifications required to the column internal, and long planned downtime result in loss of production. Also, hydraulic limitations of existing column may not accommodate increased flow. Therefore, the existing process hardware could be reused in other ways. Please sketch some of the other possible distillation arrangements. Consider also reusing existing process hardware in other prefractionator configurations. Let us look at the solutions of working section 6. Okay, for sketching of the other possible distillation arrangement, category 1. Exploiting 2 existing columns by incorporating 2 dividing wall columns in parallel. So this is category 1. For category 2, there are 3 possible options for a dividing wall column formed by linking 2 existing columns together. As shown in this slide, you have the first option, okay, whereby you have the dividing wall column at column 2. Dividing wall column at column 1 for the second option, and dividing wall column at column 2 whereby you have extra feed over here. For category 3, prefractionator arrangement without a new column can be achieved, whereby E1 and E2 are existing columns as shown in this slide. You have the top product, bottom product, as well as the side streams. Also in category 4, the peg-yoke arrangement without a new column also can be achieved, similar with category 3, whereby E1 and E2 are the existing column. The only difference here is you have the thermally coupled line. From category 4, category 5 can be achieved, whereby it is a peg-yoke arrangement with a new column. As shown in this slide, E1 and E2 are the existing column, and N is the new column. So the N new column can be arranged accordingly, depends on the sketching. You can see this one, the N column is here, okay, E1, E2, or N column is here, E2, E1, or E2, E1, and N, okay, depends on the arrangement. Similarly, for prefractionator arrangement, a new column can be added in the existing column 1 and column 2, as shown in these slides. So it could be many different arrangements in this way. Besides, the thermally coupled columns in direct and direct sequences also can be arranged. For example, as shown in these slides, okay, whereby the E1 and E2 are the existing columns, and this falls under category 7. After the many possible options for the retrophic arrangement, here come to the possible alternatives to this retrophic case studies. The alternative one is retrophic to a peg-yoke column arrangement as shown in this slide. Okay, you have the debutanizer and the isobutanizer. At the end of the day, after this retrophic, the heat duty for the deputanizer is actually 0. On the other hand, for the isoputanizer, it is 7,330. And then you have the installation of new piping over here, okay? And then the energy saving is total 28%. And it's involved, as I mentioned just now, the new piping and minor modification to column internal only. On the other hand, for alternative 2, it is a retrofit to a prefractionator arrangement by fully utilize the existing equipments of the deputanizer and the isoputanizer. As shown in this slide, you can see these two equipments already been arranged in the prefractionator arrangement. The heat duty for the deputanizer already reduced to 2,500 and the heat duty for the isoputanizer already reduced to 4,900. The total energy saving is 27%, which is only 1% lower compared to alternative 1. And also, this arrangement involves minor piping and equipment modifications. It is easy to control and operate and less high temperature heating requirement. We can achieve 3 product separations in the isoputanizer, whereby the isopropane as a top product, gasoline as the bottom product, and N-butane as a side streams. That's all for lecture 6. Thank you for your attention.